In this post, I'm actually going to take a look at a blog post that I made about a year ago that has to do with these sort of ontological entities in science that we are committing ourselves to when we come up with a theory. I'm not going to read the entire blog post, but I'm just going to read sort of this end part of it that has to do with what we are discussing here, which is sort of the ontology of the entities of our theories here. And so ontological theories tend to be slightly different and can be even more difficult to test for a correspondence with reality. And so I've made this distinction between things like procedural theories and ontological theories, where ontological theories are actually sort of proposing some kind of entity, like the wave function or a field or a potential or something like that that actually exists, where a procedural theory would be more like the theory of evolution by natural selection, which doesn't say that there's some substance or thing that's causing, mutations and the selection of of individuals with greater fitness and things like that. Those are processes or procedures occurring. They're an ontological entity. But here I'm using this phrase here, ontological theories, to sort of talk about theories that do propose ontological entities. And so here I'm saying ontological theories tend to be slightly different and can be even more difficult to test for correspondence with reality. It's the nature of these kinds of theory that prompted me to make this post in the first place. I might subdivide ontological theories into two types. So I'm calling it mechanistic ontological theories, or MOT, and interpretive ontological theories, or IOT. And so MOT, I think of general relativity, for instance, where we say that the mass and energy causes dynamic changes in space-time itself. So this is a mechanism that explains why we observe the data we do. So, for instance, the change in path of light around massive objects, gravitational waves, and so on, by appeal to a kind of substance, sometimes called the fabric of space-time. Then we have interpretive ontological theories. So think of interpretations like in quantum mechanics. So in the Copenhagen interpretation, it is not positing a causal mechanism for how the wave function collapses, but merely giving an interpretation of what's happening during the measurement. So in the many worlds interpretation is not positing a mechanism for how the universe come into existence, so how the different universes that our universe splits into come into existence. It's not giving a mechanism for that, but merely giving an interpretation of what's actually happening during a measurement. So same with the pilot wave interpretation. So our mechanistic ontological theory tends to be less controversial because these theories appeal to our intuitions. So this often characterizes such theories. So the bending of some fabric in response to a disturbance by mass or energy is something most humans can grasp, even if the mathematics of general relativity aren't understood. But what is the ontological status of this fabric of space-time? So what is the causal mechanism by which mass and energy disturb this fabric? So nothing in Einstein's field equations demand that we make this disturbed bending or flexible fabric interpretation of the underlying mechanisms explaining the data. So the same thing in quantum field theory. And so I think these mechanistic ontological theories fits well with Thomas Kuhn's idea of the paradigm. So a paradigm is a proposed mechanism or substance that appeals to our intuitions in some way. The Newtonian view of gravity posits a sort of force between objects. Gravity says that it's not a force as we tend to understand it, but in fact a curving of spacetime. So gravity in the general theory of relativity sense. But this picture of a fabric curving is in response to matter energy, so not being necessarily entailed by Einstein's field equations. could someday be overturned, even if the current data continues to be tested and verified. And so this makes me wonder how much stock we should put into the curving space-time fabric way of thinking about gravity in space-time. And so the same for quantum fields and for Lagrangians, uh, which I sort of describe here. So the interpretive ontological theory can be more controversial. So the Copenhagen interpretation, collapse interpretations, many worlds, pilot wave, and so on are competing ways to interpret the wave function and measurement problem of quantum mechanics. But we could see how this interpretive ontological theory applies to in other areas, such as the fine-tuning argument for God, for instance, where the appearance of fine-tuning in our physical constants is interpreted as either emerging from the multiverse, just being a happy accident, or as evidence of an intelligent designer. So the hallmark of the interpretive IO theory is that it permits the shut up and calculate approach to doing physics. So what the wave function actually is, or what actually happens to it when it's measured, don't matter according to this view, or at least, according to the sort of Copenhagen interpretation view. So all that matters is that the theory makes accurate predictions and can be useful. So the same goes for this should be fine right here. So fine tuning. Who cares how the constants got their values? This view says all that matters is that they do have the values and we have to be able to measure them. So the shut up and calculate approach could be used in many parts of physics. We certainly don't need the curving fabric of space-time in order to use Einstein's field equations to calculate predictions about how matter and energy will move through space and time. So one could perhaps even say that the distinction between the mechanistic and interpretive ontological theories is that the mechanistic ontological theory has interpretations that appeal to human intuition where the IoT does not. All right, so this is the part that I kind of wanted to actually get to here. So the question I've been considering has to do with what is known as scientific realism and scientific anti-realism, or what could be known as instrumentalism. So the scientific realist says that this putative fabric of space-times or fields and quantum field theories are real entities. Indeed, a popular argument by scientific realists is that it would be a miracle if our predictions were so exquisitely true and accurate if these things did not exist in some important way. So this is known as the no miracle argument, or NMA. So meanwhile, the scientific anti-realism says that these proposed objects are just useful or instrumental ways of thinking about things. This is the shut up and calculate view of quantum mechanics, meaning that we shouldn't waste our time discussing what the ontological nature of the wave function actually is. So this is popularly framed in what is known as pessimistic induction, which essentially says that every sort of ontological entity that's ever been postulated in the past has been shown to be wrong, and we have no reason to think our current entities, such as space-time fabric or quantum fields, won't go the way of the luminiferous ether, or phlogiston, where phlogiston was some explanation for how fire worked back in the day. Then there's scientific structuralism that attempts to bridge the gap between realism and anti-realism, although structuralism in science has itself split into schools of what are known as ontic structural realism, which says that the structure exists and is the ground of reality, which we could think of as the sort of famous it from bit sort of idea of reality, which you could think of as almost being sort of like the simulation theory of reality. And then the epistemic structural realism. So the structure exists, but is realized by some deeper entities not accounted for in our theories. So it from bit from it. And so we have the bit, so sort of the computations of reality that give rise to the its, so the things that we sort of experience and see. But the bits are then being computed, by some sort of underlying structure beneath that. Where this other version, so the it from bit is saying that the bits, these sort of computations, are the ground of being, that there's nothing deeper than that. And so I made this right here to kind of show this. So we have the it, the bit, and the it. So we can think of like the red here as being sort of the structure of reality we see, and then we have the bit here in blue beneath that, and then there is some sort of it even beneath that here in green, in the sort of epistemic structural realism, where the ontic structural realism would not propose this green part underneath here. So the ontological status of ontological theories, whether the mechanistic or interpretive, has been examined by people like Rudolf Carnap and W.V.O. Quine. So Carnap talked of linguistic frameworks, where the ontological reality of a theory is an invalid attempt at an external view of the theory. So I'm not going to read through the entire quote here, but I'll skip down to here. So the internal question can say nothing of the ontological status of its subject. So when you're talking about a theory from within the framework of the theory, then we have external questions can only pertain to the utility of the theory. And so what Carnap is saying is that you can't sort of from outside the theory judge the ontological status of things from within the theory. The only thing you can do from outside the theory is judge the utility of the theory, so not its ontological status. So this view has always struck me as the shut up and calculate approach in science. So in quantum mechanics, the Schrödinger equation, for example, gives the linguistic framework for answering internal questions. So what is the probability of getting a particular result would be an internal question. The external question is whether or not these predictions are useful for whatever it is we want to apply to quantum mechanics. So to even ask whether it's a pilot wave or a split in the universe is invalid under the sort of Carnapian view of things, because these things are outside the linguistic framework and do nothing to tell us about the utility of quantum mechanics. So Carnap was famously a logical positivist, sometimes called a logical empiricist, and so had no patience for such navel-gazing sorts of questions as what things actually are. So Quine, on the other hand, talked about ontological commitment. And so I'll just read this part here in bold. So a theory is committed to those and only those entities to which the bound variables of the theory must be capable of referring in order that the affirmations made in the theory be true. And so essentially it's saying that the sort of ontological entities that we are sort of committed to saying are real are just the things that sort of help the theory. Or to oversimplify, if your theory requires that some entity or substance exist in order for the theory to work, then you were committed to the ontological existence of that entity or substance. You are not committed to any entities or substances that do not alter the sorts of predictions your theory makes. So in other words, don't add unnecessary entities or substances to your theory. So I'm saying that this works well for the mechanistic ontological theory, but perhaps not always for the interpretive ontological theory. But even if applying it to the mechanistic ontological theory, we are shying away from the question of whether something, say the fabric of space-time or quantum fields, actually exist as real entities or substances. So just because we need to commit ourselves to its existence for the theory to fully work says nothing about its actual existence. It's impossible, or it's possible rather, that neither Carnap nor Quine would say that there is not some fact of the matter, some truth value to, say, the proposition space-time is a substance X. But what they both might say is that at best such questions are unhelpful and unknowable. Some might see these attitudes as defeatist and even unhelpful. Thinking about such questions as what is there can potentially lead to progress in science that would not be possible by taking the shut up and calculate approach. Others might see it as useful because people don't waste their time pondering unanswerable questions. And so I kind of get into my own view here, but those were the things I wanted to sort of discuss here that are relevant to this video series. Is this sort of idea of like the scientific realism and anti-realism and the sort of ontological entities we are committed to. And so, in the, I guess, Quinean view of quantum mechanics, we're committed to this wave function as being sort of a real thing, but that's just because it's what is required for us to actually, make these predictions. We're committed to a probability wave because that is sort of what the Schrodinger equation posits as being real, and so we're committed to it. But this right here is kind of the I guess takeaway message from this video is this sort of idea of scientific realism versus scientific anti-realism or instrumentalism, and that is kind of the crux of the ontological issue in quantum mechanics is like what entities are we actually committing ourselves to, and what entities can we say actually exist, what entities are real, and should we say that they're real, or are we, should we sort of just succumb to pessimistic induction and say, well, we might say they're real now because, in the Aquinean sense, we're committed to them, but they're not actually real. We shouldn't say they're actually real because, so many things in the past, like the luminiferous ether or the phlogiston, have been shown to be wrong, and we have no reason to think that what we're positing now as entities might also be shown to be wrong in the future. But anyway, that was a little bit of an aside from the book that I'm following on here, but I thought this was an interesting topic to discuss as it relates to quantum mechanics and sort of the ontological problem of quantum mechanics. But anyway, I hope you found this video useful, maybe at least interesting, and I will see you in the next one.